Good morning to you all, and welcome to this webinar on automated flexibility management of buildings with focus on the technical results from the iFLEX project. My name is Louise Riley, and I'm here together with others from the iFLEX team. So we have Jussi Kilianda from VTT Technical Research Center of Finland, researcher Davut Topalovic, and senior researcher Dusan Gabrielcic, both from the Josef Stefan Institute in Slovenia. Present is also Jesper Testrup from INJET, who will be managing all your questions. So we invite you, if you have any questions during the presentation, please ask them in the question option you will find in the toolbar. I should also say that this webinar will be recorded and may be available on demand, so you can revisit any sections of the webinar that you would wish to. So a few words on the agenda. I will briefly introduce the iFLEX project, and then we'll move into the presentations by Jussi and Davut on the automated flexibility management and the technical results from the iFLEX project. And then we'll end up with a Q&A session answering any questions you might have. We hope to be able to answer all your questions, but if not, we can promise to send you answers afterwards, but we'll try to make sure that we answer most questions. So moving on to a short introduction to iFLEX. The aim of iFLEX is to unlock more demand-side flexibility tailored to the needs of a renewable dominated energy system. And we do this by enabling small-scale residential households and buildings to participate in energy flexibility schemes and demand response programs. So this can happen either explicitly acting upon requests from the power grid, or it can be implicitly reacting to price signals. To make participation easy, the project is developing an intelligent software assistant called the iFLEX Assistant that manages the energy flexibility in an automated way. So the assistant creates a digital twin of the building, and it operates the building on behalf of the occupants' preferences. So either preferences in terms of comfort, energy cost, environment, and also wishes for automating the management. It then offers the flexibility to power grid management for power grid management purposes. So moving into the presentation now with Jussi and Davut, who will go into more detail on the iFLEX approach to automated flexibility management, and also adding examples from the pilot sites in iFLEX, so the pilot sites in Finland and Slovenia. So Jussi, the word is now yours.
Okay, thanks, Louise. I hope you can see my screen now.
Yes.
Okay. So here's the outline for the webinar presentation. I will first give you a short introduction to the topic, explain a bit more in detail the iFLEX Assistant concept and our key ideas and approach for the hybrid modeling and automated flexibility management. Then, like Louis said, we will dive a bit more in detail with the pilots and what type of approaches we have applied there. I will present the Finnish pilot, and then Davut the results and approaches from the Slovenian pilot. And of course, in the end, we will provide some conclusions. So we all know that demand flexibility is becoming more and more important for the power system balance. And this is because as we replace traditional fossil fuel-based power plants with renewables, we kind of lose controllability that then needs to be compensated with demand flexibility. Two of the most potential assets for flexibility management are heating systems or HVAC systems in general, and then EV charging. And in our work, we have mainly focused on the heating systems. Heating systems have a lot of potential, and actually they are the most potential technology in the near future, according to a recent study by DNV. And this is because heating systems use a lot of energy, and buildings also have a large thermal mass that can be used to store energy and this way move the consumption within a day. For example, to periods when there's a lot of renewable production available. Of course, electrification of the heating systems need to happen before the flexibility is available for power system balancing at a large scale. But this is actually now happening quite rapidly in EU, and there's a plan for 10 million new heat pumps in the next 3 years. In some countries like Finland, we already have a lot of electric heating available. So for example, you can see from this figure on the right that in 22 we had roughly 5 gigawatt of electric heating. It's the kind of outdoor temperature dependent part of the demand in Finland, and this is roughly half of the average power demand during the winter. So these electric heating systems, both direct and then of course heat pumps, are popular outside of cities in Finland. In cities we mainly have district heating, but because of combined heat and power plants, it's also possible to use the heating systems supplied by district heating to provide flexibility for the power system. And in the later part of the presentation, I will show some results in the case of Finnish pilot, where we actually have a hybrid heating system that is both supplied by district heating and an exhaust air heat pump. There are of course several challenges that need to be solved before demand flexibility from buildings and heating systems can be used for power system balance at a large scale. The first challenge is that the demand side assets need to be very predictable. So we need to be able to forecast the baseline and flexibility, of course, including all rebound effects that will occur when we take the flexibility into use. And this is important if we want to use demand flexibility as a key balancing asset in the power system. Another challenge is the controller design. And this is a challenge because HVAC systems are complex. There are long feedback cycles and many times nonlinear dynamics. And now the controller, in addition to this traditional thermal comfort, it should also take the dynamic prices, local production from renewables, coefficient of performances, maybe power tariffs. It needs to take different things into account, and we believe that the model-based approach, model predictive control, will be needed to realize this in an optimal way. And the third challenge is of course money, and in this case mainly the cost of deployment. And this is important because the benefits that we can obtain from a single building are limited. So the modeling and all integration with home and building automation systems and metering infrastructure needs to be automated so that the demand flexibility can be a sustainable business at a large scale. So like Luis already explained, the iFLEX Assistant is the key concept of the project. It's a software agent that automates flexibility management in buildings and in consumer premises to maximize the consumer benefits. Typically, this means reducing the costs and maybe maximizing or reducing the CO2 emissions while keeping the thermal comfort and other preferences in check. The iFLEX Assistant has 3 main functions. First function is to, of course, ensure that the flexible assets like heating systems and EV charging are operated according to the consumer preferences. The second function is to provide aggregators and in some cases utilities with forecasts on the baseline load and flexibility. And third, the iFLEX Assistant is responsible for controlling flexible assets to maximize consumer benefits while taking into account dynamic prices, incentives, and explicit control signals from aggregators. In this slide, I try to highlight the main ideas and approach for automated flexibility management and optimal control. The key idea kind of highlighted here is that we use hybrid modeling. So we try to combine the best parts of machine learning and physics-based modeling to create models that are accurate and robust, but also easily replicable to new buildings and sites. And these models that we create with this hybrid modeling, they form what we call a digital twin of the consumer. And the automated decision-making algorithms, model predictive control algorithms, use these models to find the best control policy for, let's say, heating systems, EV charging in any given situation. And like I said, we use model predictive control, which means that the optimal control algorithm optimizes the set points for different devices and control points in a sliding window. And new optimization is performed at every time step. In our pilots, we have used mainly 60-minute and 15-minute time steps for the model predictive control. And from this optimization, we get the set points, but also the forecasts or plan for the baseline load that can be sent to the aggregator. We can also use the models to estimate the minimum and maximum load and calculate the flexibility at different time periods, and also provide the aggregator with this information so that it can be taken into use in the when the aggregator bids in different markets. And of course, the iFLEX Assistant will also use the models constantly to perform local optimization, trying to reduce the costs of the consumer. Okay, so like I said, our hypothesis is that by combining the best parts of machine learning and physics-based modeling, we can create models that can adapt to data and provide state-of-the-art results. But also the models need to work in situations that are not covered in the training set. And it's also important that the model creation is automated. So our approach there is to apply automated machine learning together with physics-based modeling to automate the model creation process. It is still an kind of open research question that what's the best way to combine machine learning and physics? What's the best way to create this hybrid model? And here I have listed some approaches for hybrid modeling that we have studied in the project. We will not go into details with all of these, but we will describe the bolded approaches briefly in the context of Finnish and Slovenian pilots. The gray box modeling here, it's a typical approach to represent building heating dynamics as a kind of circuit theory model, which consists of resistive and capacitive components. Our new approach here in this project that Davor will present in the context of in the Slovenian pilot is that the gray box model is implemented as a neural differential equation. Neural differential equations are a quite new model type, which allows differential equations to be embedded into a neural network, and this has many advantages. In the Finnish pilot, I will show a bit different approach where we augment machine learning model forecasts with simple resistive RC models during a demand response event. It's also important to understand that the modeling approach is directly linked to the optimization or the model predictive control method. So if we have like linear models, like typical gray box models, it's possible to use traditional linear programming methods to find the optimal set points, for example, for a heating system. But with these other approaches, we typically have to rely on simulation or search-based optimization methods, like the Monte Carlo tree search, for example. So there is a kind of trade-off whether you choose a simple model, linear model, and then kind of optimal control algorithm that can be proven to be optimal, or whether you go for maybe more accurate, more detailed model, but then you have to rely on more heuristic-based, non-optimal control algorithms. And this is also like an open research question, that which of the approaches will actually provide the best results in practice. Okay, then the kind of final slide from the overall approach part before we go to the pilot. So here is a kind of functional architecture of the iFLEX Assistant. I will not go through everything, but focus mainly on the central components here that have the main responsibility in the automated flexibility management. So the automated flexibility management module is divided into two types of entities. There is the energy planner here, and then one or more controllers here. And there's a single energy planner component which is responsible for optimizing the load profiles and estimating the total flexibility at the building level. And to realize this, the energy planner uses model predictive control with the hybrid models available in the what we call a digital twin repository. In addition to the energy planner, we also have controllers, and there is a single controller for each flexible asset. So for example, we could have a controller for the heating system and then another for EV charging. And the role of the controller is to follow the kind of flexible asset specific load profiles provided by the energy planner. And if you are familiar with the ongoing European and international standardization, we can kind of map the energy planner and controller to these entities. So the energy planner is very similar to the customer energy manager, and controller to the resource manager entities in the standard. Okay, let's then jump directly to the Finnish pilot and kind of a bit more concretely the approach is there. In the Finnish pilot, we actually have two bigger buildings, an apartment building depicted here and a supermarket. But in this presentation, I will just focus on the apartment building, iFLEX Assistant. The main flexible asset of the building is the heating system. It's a hybrid heating system that is supplied both by district heating and an exhaust air heat pump. We collect a wide variety of data from the building automation system and are able to adjust the set points for two different control points. The first control point here actually is the water temperature used for space heating, and this is our original control point. It can be used to constrain the space heating circulation, how much energy goes to the space heating. Later, we also implemented a control point directly to constrain the heat pump, because we were not able to control the heat pump as we would like with the space heating control point. Here is a simplified system architecture for the whole Finnish pilot. We implemented it together with the pilot together with Caverion, which is a building automation and facility management company, and Enerim, that's an aggregator, and provides services for utilities and retailers. Additionally, as part of the Finnish pilot, we organized a common pilot with OneNet project, where we demonstrated how the flexibility from the pilot building together with large number of virtual sites can be used for solving bottlenecks issues in the DSO and DSO networks. And this common demonstration with OneNet was implemented together with Fingrid, which is a Finnish DSO, Kymenlaakson Sähkö, which is a DSO, and then Nord Pool, of course, in addition to the iFLEX partners. And we have the iFLEX Assistant integrated with Goverion's automation system through Chase Gateway. The connection to Enerim's aggregation platform is implemented through MQTT. The iFLEX Assistant provides the aggregation platform with baseline and flexibility forecasts, which are used to make bids, or were used to make bids in the Nord Pool intraday market. As you can see here, we also have implemented a variety of monitoring tools to visualize the baselines, both for electricity and district heating, and also the flexibility available at different time periods. And also a tool to monitor the data that we collect from the building automation system. Okay, this slide tries to illustrate the hybrid model that we have implemented for the apartment building a bit more detail. So like I explained earlier, the key idea is that we use machine learning models to forecast the baseline and then augment these forecasts with physics-based, simple physics-based models during the demand response events. We have a simple, also a simple physics-based model to model the impact on the indoor temperature when we constrain the heating, and this model is derived from the Newton's law of cooling. It has two parameters: a thermal capacity for the whole building and a heat loss coefficient. And the heat loss coefficient we can identify from historical measurements using the energy signature method. I will explain this a bit more in detail in the next slide. And then for the thermal capacity, we require control experiments for proper identification. So actually, when we started the pilot, we used initial values based on standard estimates that are calculated based on the floor area of the building. Here is how we identified first of all, the heating demand and also the heat loss coefficient of the building. So we automated the energy signature method for identification of the total heat loss coefficient. In the energy signature method, you need to fit a linear model to the heating demand, and then as a function of the outdoor temperature. And the heat loss coefficient H is then the gradient of the line. So we assume that it's linear, and it's typically is if the coefficient of performance remains the same. And in this case, we identified the heat loss coefficient to be a bit over 4 kilowatts per Celsius. So this means that if the outdoor temperature drops by 1 degree, the heat demand on average increases by 4 kilowatts in the building. We had a bit of a small challenge in automating this process because the data we had, there was some issues. So there has been issues with the heat pump of the building, so that there are a lot of periods shown here. These are daily averages. So a lot of periods here when the heat pump has been off. So we needed to first use a clustering algorithm. We use a Gaussian mixture model to first cluster the data into two groups and then fit the model there so that we can actually have a proper fit to the data. And of course, the gradient of this should be the same, and that was the case. So yeah, we were able to identify the heating demand as a function of outdoor temperature, and then the heat loss coefficient, which is required in the indoor temperature model. This heating demand is part of the hybrid model of the building. Then for the thermal capacity, we actually calculate an initial estimate based on standard values and came up with based on the floor area 720 kilowatt hours per Celsius or Kelvin, and then to actually find it or correct this value based on data, during the pilot we also organized control and demand response testing and used these results to have a better estimates for the capacity. And the capacity was then calculated using this equation. This is also derived from the Newton's law of cooling. And we assume here that there's no heating going into the heating system. And then as we know the age, we need to measure the outdoor temperature and then the change in the indoor temperature. And then we can calculate the heat loss coefficient. And based on the data, we calculated the heat loss coefficient to, the thermal capacity of the building to be roughly 430 kilowatt hours per Celsius or Kelvin. So it means that if the demand is roughly 100 kilowatts, you can fully turn off the heating for a bit over 4 hours. And in this period, the indoor temperature only drops 1 Celsius. If you allow the indoor temperature drop 2 Celsius degrees, then it's like double the flexibility is double the capacity here. Okay. Yes, like I said in the motivation part, it's important that the iFLEX Assistant is able to provide the aggregators and also utilities with accurate and robust baseline and flexibility forecasts. During the last 2 winters, last 2 winters, we have executed more than 50 demand response events, both to constrain the space heating and also the heat pump directly. And we have measured the accuracy of the forecasts provided by the iFLEX Assistant. In our pilot, the forecast length was 24 hours. So we mainly targeted for the intraday market, and the iFLEX Assistant provided a new forecast every 60 minutes. And also when we activated the flexibility, new forecast was also immediately calculated. And we calculated the errors using root mean square error, and for district heating, the error was a bit below 8% or roughly 8% when normalized with respect to the variation, so minimum and maximum values. And for electricity, the accuracy was roughly 6%. Here on the right side, you can see some individual forecasts from periods that actually include these DR events. And here on the top, you can see the district heating forecast, and on bottom the electricity forecast. And the forecast is represented in blue and the measured values in orange. And in this example shown here, we have a DR event ranging from 8 to 9. And at this point, when this event was executed, we only had the control point for the space heating available. And you can see that there is no impact on the electricity demand. And in these first experiments, this was a bit surprise for us. And it happens because the heat pump is get active by domestic hot water heating. And there's also a small hot water storage for the heat pump. So even though we constrain the space heating, typically you don't see any impact here. So because of this, we added the possibility to control the heat pump also more directly. And here you can see some more examples. Here in the first pair, this example is still with the space heating constraint control. So we have actually two events a day here. In the middle figure, you have actually 2 events happening here. There's a longer DR event during the night from 2 to 7, just for the space heating, constraining the space heating. And here there's an example where we constrain both the heat pump and then the space heating. And in the last figure, we selected the period where the deer event forecast had a bit larger error compared to a typical situation, and it seems here that this is mainly because the errors in the baseline forecast. So here there's one event that slightly affects the district heating, but mainly the heat pump, or this is the total electricity consumption actually. So here we constrain both the space heating and the heat pump. Okay, then final slide from my part. In addition to this explicit demand response and offering the flexibility to NRIM's aggregator platform, and from there the intraday market or test market, we also did some local optimization. The pilot building did not have a spot price contract, so we were a bit restricted in what we can do. But in any case, the iFLEX Assistant was configured to reduce the energy consumption by using the flexibility so that the indoor temperature, it tries to keep the indoor temperature as close as possible to the minimum values or the set point values. We performed the optimizations every other day, mainly during the night and morning and midday, so that we don't impact the kind of reference period results. And you can see here that we were able to reduce the costs and CO2 emissions roughly 9 to 10% during the test period. And this test period was organized several months during the last winter. Okay, that was the Finnish pilot in short, and how we have applied the approaches there. And now I will move the floor to Davut.
Hello everyone, Davut from Joseph Stefan Institute here. So far, it is clear for us that the baseline prediction cannot just rely on the machine learning and deep learning models. Instead, we should opt for hybrid modeling, which includes developing the robust physics-based models. And here I will briefly present some current results of the JSI research team on this topic. The physics-based model that we are utilizing is the 5R1C model from the 2008 international standard for energy performance of buildings. It is an OD-based framework that allows for calculating the energy demands on hourly level. This model, even though explicit and simplified, is very hard to define. As it depends on many physical and thermal characteristics of the households that are very hard to define, that are very hard to measure and approximate. And this is especially a problem if we consider applying the solution on a large scale, where it is just not efficient and nor profitable having to measure the parameters for different buildings and households out there. And this is why our focus at JSI is on developing the automated thermal model identification method. The approach that we're developing on thermal model identification is based on the neural differential equation algorithm. It is a powerful algorithm that combines differential equations and neural networks and is capable of learning the dynamics of the system based on the system's observations and the forward and backward paths. To utilize the algorithm, we have adjusted the original ODE, 5R1C ODE for thermal mass. We have adjusted it for the inside air temperature and constrained ourselves only on a nighttime case, for which certain variables that are very hard to measure converge to zero, and other variables are very easy to approximate. So the basic idea here is to observe the temperatures for the defined nighttime case, model the derived ODE with the neural network, and infer its parameters by fitting the neural OD. And then we use this method effectively narrows down the possible values for the parameters. And we use those parameter ranges further as an input to the final and third step, which is the neural OD fitting. This step considers fitting the observed temperature curves obtained from the first step by constraining the search space, the parameter search space, with the classified parameter ranges. After performing fitting for multiple nights, we average the inferred parameters and get the final set of the trained parameters that now allow us to define the thermal model. And once we have the thermal model, we can proceed to flexibility prediction. To test our procedure, we have some initial results. The test was conducted on a household located in Slovenj Gradec in Slovenia. And first, we have observed the normal, as you can see on the right side, we have observed one normal operation night and extracted the data from it as temperature observations, average heat output, average outside temperature, and etc. Besides that, we have also applied a so-called, as I said, constrained heating process, where we cool down, where we constrain the heating for a certain period and then heated the household back up. This process of cooling down the household and then heating back up allows us to collect certain data as the temperature observations, temperature drop, time cooling, time heating, and average outside temperatures. And this data is very rich for explaining the thermal behavior of the household. Once we have collected the data, we use the data, as I said, in the classification step. We classify the parameter ranges, and we fit different nights with neural OD algorithm. And here we present some initial results on the first trainings. Here, as you can see on the table at the top, here we can see the relative error for the trained parameters. We can see that the relative error varies from 1% to 20%. One remark I should make here that not every thermal model is not equally sensitive for every parameter. So this is not the most important thing that we should look when we obtain the parameters and when we want to further validate the accuracy of our model. To proceed further to the validation of our model, we have compared the total heat consumption and the average heat power for different months. And here we can see that the relative error for the trained parameters varies from roughly 11 to 21. Also, very interesting here is on the right side, you can see that we not only compare, we use the defined parameters, we use the trained parameters for the thermal model, and then use the thermal model prediction to evaluate the trained parameters. However, on the right side, we can see the forward pass on that is the prediction directly from the neural OD. And we can see here that the neural OD with the trained parameters, which is presented with the dashed red line, is indeed capable of learning the dynamics. We can see that of course, it is not perfect. It doesn't perfectly fit the temperature observations, but it is for these trained parameters, it is indeed capable of predicting the air temperature. Now, once we have the trained parameters, we can proceed to the flexibility predictions. For this, we have performed both nighttime and daytime flexibility tests, which include applying certain processes on the household and then comparing the electricity and heat consumption of such processes with the baseline prediction from the model. It is important to note here that these processes that we apply do not violate the temperature comfort, which is defined and specified by the household tenants. And what we can see here is the following. The first graph shows the heat output. The second graph shows the heat output. The second graph shows the electricity consumption. And the third graph shows the air temperature, and the fourth graph shows the outside temperature. For this particular nighttime case, we have applied a constrained heating from 7 at night till 4 in the morning, or until the upper temperature limit was reached. And then this was followed by heating back up the household until the initial temperature was reached. The thing that we're interested in here is actually how much the flexibility was achieved for the period of the constrained heating that we can see right here. We can see that for the period, for the period of the constrained heating, that is for 8.4 hours, the household was cooled down only by 1.3 Celsius degrees. And with this, we gained the flexibility of 16.3 kilowatt hours, or in terms of the power, it is 2 kilowatt watts. Also, in terms of the electric consumption per 1 degree temperature change, it is 12.5. On top of that, we also compare the total heat and electric energy consumption with the baseline prediction. And we get that for the applied processes, the heat demand was 23.01% less than predicted. And in terms of the electric energy, we consumed 15.07% less than it was predicted by our thermal model. Additionally, we also test the flexibility prediction for the daytime, where the objective of the test was to actually inspect how much of the solar energy can be used for heating the household. Therefore, what we've done is the following. From 5 till 8 in the morning, we have constrained the heating, where we stopped the heating. Then from 8 till 3 in the afternoon, we overheated the house by setting the high set point. And then from 3 till 10 at night, we again constrained the heating. Again, what we're interested in here is the flexibility of the overheating period, which is defined by this additional amount of energy that we actually managed to store in the household for this period. And for the overheating period, which took 7 hours, we managed to increase the temperature by 1.3 degrees. And we managed to harvest the negative flexibility of minus 2.33 kilowatt hours. In terms of the power, electric power, that is 0.33 kilowatts and minus 2.22 kilowatt hours per 1 degree of temperature change. Again, in addition to this, we also compared the total heat. We also compared the total heat energy with the predicted one, and we get that with this applied process, we save 37.65%. That is, we demand less, this much less energy with these applied processes. In terms of the total electric consumption, we save 36.84%. Also, I should just say that here the third graph actually shows the this household was equipped with the PV panel, and we also here show the electricity generated from the PV, and we can see that this small fraction of the electricity generated from PV is actually able to supply this whole electricity demand right here that was enough to overheat the household. Also, one remark that I should also make here is that our thermal model prediction only takes into account the outside temperature. And this is can be considered as a rough estimation. In the future, we also plan to integrate the internal gains and the solar gains, so the prediction, so the thermal model prediction will be more accurate. That's it from my side.
Okay, let's then move to the conclusions. So to summarize, heating systems, HVAC systems in general, are a good asset for demand flexibility. Of course, because of the high energy demand and natural thermal mass in the buildings. And like we presented, it's important to have accurate and robust forecasts, both for baseline and flexibility available, so that the aggregators and utilities know what will happen when the flexibility is used, so that flexibility management needs to be highly predictable if we plan to use demand response or demand side flexibility management as the core asset in the power system balancing. As we have shown, a good approach for HVAC system modeling is to combine the best parts of machine learning and physics-based modeling and apply this hybrid modeling. And we have shown a good results, let's say good initial results, and how the hybrid modeling can be done. Also some results also from the optimization side, but it's still an open research question. What is actually the best way for hybrid modeling, especially when we take into account the optimal controller design, as like we discussed, they depend on each other. In addition to this research, in the future we will also need to focus more on the scalability and replication. We already have some results on the automation side, but it still typically requires some manual work, especially with integration to the metering infrastructure and automation systems, but also on the modeling side. So that's also a thing that we will focus on in the ongoing and hopefully future projects. So thanks. Now I think it's time for questions, or I will give the floor to Luis.
Thank you very much, Jussi and David, for the presentation. Yes, we are moving to the Q&A session. So Jesper, have you received any questions? So
yes,
the first, yeah, you see it. Okay, yeah, go ahead.
Okay, so there's a question on the what is the time horizon for commercial deployment of the iFLEX Assistant, considering the challenges in interoperability from technology and standards that you presented? Yeah, this is a good question. Of course, well, there are many things that kind of need to happen. One big thing, of course, is this electrification of the heating systems, which is happening now rapidly. And other thing is kind of the standards, that it would be ideal if all building automation systems, all platforms interfacing with buildings have the same kind of interfaces to get the data, and this way it would make it easier to automate the deployment and all of this. But kind of the in Finland at least, demand flexibility in terms of spot price optimization is kind of happening already. There's some like manufacturer specific solutions available, and I think with bigger buildings, we are, for example, also working with supermarkets in the pilot. So there it's a bit more harmonized. So with bigger players, bigger buildings, I think it's possible in also shorter time frame, like let's say 1 to 5 years after the project. But then to have a solution that is scaled to the whole Europe, all households with heat pumps and so on, I think that will take probably a bit longer time and so on. But it's quite difficult to estimate. But I think it can happen, and it kind of needs to happen also in the near future. So 1 to 5 years, I would say, is my optimistic estimate. Yes, we don't have other questions, or Okay, there's another. Can the modeling methods Davut presented be used for larger buildings? I could answer, but I will give the yes.
In our case, yes, because the standard that we're using actually has a method that considers multi-zones. But in this standard, it's very, let's say, simplified. That, for example, if the temperature inside the whole building, larger building, doesn't change more than 4 degrees, it can be considered as a one large thermal zone, basically as a one large household. So I would say yes, with some approximations, but also with the multi-zone approach.
Yeah,
I'm sure. Yeah, regarding the neural OD and the differential equation, whether it gets too more complex than the just on the household level, but I think it definitely has some space for improvement, and it has some potential.
Yeah, I think it can. There's actually not, well, of course there's differences, but in principle the approaches that I showed and then what Davut showed, the core physics are the same, and there's just kind of some differences in details how they are implemented. And I kind of like a lot the neural differential equation approach, because in theory at least it's possible to combine the machine learning part and the physics part into one model. For example, in the Finnish model I showed, we have like a simulation model where there's parts are pure machine learning models and then parts are these hybrid models that are learned from data. But with these neural different equations, I think it's a nice that it can be kind of the model can be fitted end to end and handled as a one neural network with differential equations inside the model. So I think it's just a double question on how detailed you want to model the physics part. I think that's the main question then.
That's the main question, yeah. Machine learning stays the same, yeah, but the physics-based model will change, and yeah, it's just how complex you want to make it.
We are waiting for more questions.
Yes, if there are more questions, or else we will continue. Okay,
there are no more questions.
Okay, thank you very much. So this will then leave us with a big thank you to everybody participating, especially the presenters, and for you attendees being interested in this webinar. As I mentioned, it will be available on demand in case you want to go into detail on the specifics. I can also say that if you're interested in joining another webinar that we are planning, we have the next webinar on 20th of March. And this will deal with the consumer and prosumer user engagement in iFLEX and the results from the project with relation to this. So with these words, I would like to thank you again, everybody, and have a really nice day. Thank you.
Thank you. Bye-bye.
Bye.